Good morning and good evening, everybody. Welcome again in renewable energy and water for the USA and Serbia. I'm Ivana Validzic, research professor from Laboratory for Atomic Physics at Vinci Institute of Nuclear Science. And although I presented myself very shortly in the beginning, this is something from my work experience after the finishing the Faculty of Physical Chemistry at the University in Belgrade. I was research assistant at the same university, and then I finished my PhD at Van Hoff Laboratory in Deba Institute of Nanomaterial Science in Utrecht University in the Netherlands. Then I returned here and basically I from the Institute of Technical Science of Serbian Academy of Science and Art, I changed in the Vinci Institute of Nuclear Science. And I was first assistant research professor, then associate research professor, and from 2013 I was research professor at Vinci Institute of Nuclear Science, which is the same level as professor at university, just in the institutes, the research is primary compared to the university where the teaching is primary. So welcome to something that I will teach in next 4 lesson, and that is photovoltaic, an introduction, solar cell for the energy solution. Basically, I know that we had a nice picture of the solar cell and photovoltaics, but also behind of this nice picture of the solar cell and everything else, there is also and the physics. So basically, something like a photovoltaics and introduction, I'm gonna divide it in four separate lecture. And one of first I'm gonna teach you today is solar resource and semiconductor. And then we're gonna teach in the next one, transport and carrier concentration in semiconductors, doping in semiconductors, controlling carrier density. Then on the third lecture, we talk something about the PN junction and light absorption and the photovoltaic effect. And the last units will be about the solar cell and advanced solar cell design and next generation solar cell. So the first one, basically concerning the solar resters, we're gonna see and we're gonna talk about how the solar spectrum look like, how the sun delivers energy. Then we see how the solar spectrum is very replicated by when compared to the black body radiation. Then we see how much energy does the sun deliver. Basically delivers a lot, but we will also see that it's going to take quite a bit of a year to meet all energy needs. Then we talk about the atmospheric effect, which decreases the amount of available radiation on the Earth surfaces, but still a lot remains. And then we talk about the distribution of solar resources and the photon flux. So how many photons at each energy came from the sun? An important effect when we calculate basically efficiency of our solar devices. And then we talk about the semiconductors, which is a critical component of a solar cell and semiconductors physics. I really try to combine from whole semiconductor physics only, which is quite important for you for understanding of the semiconductors and the process in the solar cell and everything else. So only very important stuff like is crystalline structure, electrical transport, such as resistance, resistivity, and conductance, then material classification in terms of metals, insulators, and semiconductors. We talk about the conductivity, mobility, and carrier density, and electronic states from quantum mechanical point of view, then energy occupancy and the bands. We saw how they look like picture of the free electrons, also from the perspective of the quantum mechanics. Then we talk about electron energy and momentum, the density of electronic state, then about the filling, occupancy of electronic states, probability of being occupied by Fermi-Dirac distribution. Then we talk on the end about the semiconductors and the band gap, electrons in the conduction band and hole in the valence band, and generally about the electrons and holes. So let's start from the beginning. So when we talk about solar spectra, we defined in the beginning something which is which we call solar irradiance, and we put them, this is the solar irradiance for the A from lambda. It's equal, basically it's proportional to the power, and from over the area over the length. Length we mean by the wavelength, and basically solar irradiance we define as amount of the power delivered per area per unit wavelength range. And if we now imagine the Earth and also some unit area which is situated above the atmosphere, so we now don't watch the atmospheric effect because we are above the atmosphere. And then we watch some sunlight beam, they coming to this unit area. That's what you can record it. And this is the basically the dependence of the solar irradiance in a function of the wavelength. As you can see, for example, this red curve represent the solar spectra. That's something that you can see, for instance, if you sit above the atmosphere, a keeping detector and record everything what is coming from the sun. We call that IM0 because that's concerned the air mass, which is 0 and which is no atmosphere. That's why we said it's above the atmosphere. Now we should define something which we call the solar constant, and the solar constant usually represents something which is which we call the total energy flux, which is the energy per time per area incident on the unit area perpendicular to the beam outside the Earth atmosphere. And if we integrate this basically irradiation, so we're gonna get how much is that solar radiation above the Earth atmosphere. This, and which is here you can see 1,367 watt per meter square, or around 1.4 kilowatt per meter square. These dotted lines here represent the integral. And here you can see basically that's by integration you get something like it's 1400 or 1.5 kilowatt per meter square. And now the solid line here, which you can see, expect the spectra of the sun without the atmosphere, is basically the spectra of the black body radiation observed at 5,960 Kelvin. And as you can see, this spectra perfectly fit to the solar spectra without atmosphere. So what means basically the solar radiation to the black body on this very high temperature? So basically everybody on some temperature emits some radiation, and we find basically by the equation which is derived by Max Planck, that on this temperature on almost approximately 6,000 Kelvin, basically this spectra perfectly match of the spectra of the sun. And as you can see, this Max Planck equation, it's look like this. So the first part is basically the density of the photon modes connected with geometry in conversion, and the second part is second part of the equation. It's concerned the occupation probability, where here you have mostly only constant F of S. It's basically concerned the solid angles subtended by the sun from the Earth. This is basically if you look the sun from the sun point of Earth, you're gonna see some disk, and that's basically that's angle that you can provide by the thickness of this disk. We call the solid angle sustained by the sun from the Earth, and this is the constant. And here you can only hear by the constant. This is the Planck constant, and this is the Boltzmann constant. And this is something that we call. We go further because we define the solar constant, which we said that we call the total energy flux, and we said how big is it. Now we want to see how it looks like, how much is that energy how much is average energy flux per unit area per surface. And if we take the Earth intercept on area, we can represent this as a PS square, where R represents the radius of the Earth. Then the total power intercepted by the Earth will be solar constant times area. And this is distributed over the total surface area, which is we usually calculate as a 4 pi r squared. Average energy flux, which is incident on the unit surface area, we're gonna get by divided these two expressions, and which will be 342 watts per meter square. This corresponds to an annual average, which if you multiply by the 365 days per year and 24 hours per day, you get something like a 3,000 kilowatt per meter square per year. I find this data that, for instance, if you want to satisfy all energy needs, I find this data concerning USA, if you want to satisfy all energy needs from the solar spectra, then you need something like 11.3 kilowatts, which is also 100,000 kilowatts per hour per year. If you compare 100,000 and 3,000, you're going to see that you need a lot of meter of solar cell to satisfy all energy needs. But this is only for the solar. Now we're going to see how the spectra of the sun is changing if we combine also atmospheric effect. So we can again integrate the same solar constant and the same spectra. So this is the irradiance to the increment d lambda. Just we now take the Rm air mass, which is 1.5. And if you integrate it, so this is the green dotted line for integration if you include the atmosphere, and the red dotted line is integration as we previously see on the slide for the AM0. And here you can see basically the previously for the AM0 without atmosphere, we get something like around 1.4 kilowatts per meter square. And for AM, I'll return rate later to explain what is AM 1.5. We get basically 1 kilowatts per meter square. And we see that the reduction due to the atmosphere is somewhere around 27%. So this is a not small reduction. And I know, for instance, that in the past, it was basically idea that maybe the solar cell we can replace above, we can put above the atmosphere, because it would be nice. You have all the time radiation, so you don't have a shadow effect. You all the time you have a radiation, there is no cloud, and but I don't know what has happened with this idea. Probably is quite expensive, but it was one of the idea. And now I return just for a second. So we see that basically the solar spectra can be presented as in a function of the irradiance from the sun, in a function of the wavelength. But this spectra can be also presented and on the different way. We can present the solar spectra as a photon energy. And here we see basically that the solar spectra as a function of the photon energy can be presented as the power per area per energy. So which is basically the same as the irradiance, just here we replace the wavelength by the energy, because we discussed in the form of the photons. And if we basically use this equation that the irradiance is the same as the photon energy, so the E lambda, we call that power per area in the wavelength in increment d lambda. It's the same as the power per area in corresponding photon energy increment dE. This minus is putting here because if your lambda increases, then your energy decreases, and opposite. If lambda decreases, then energy increases. And here you can, for instance, see that here is the basically period or the function of the photon energy. So you can just put from this equation. And if we use that the energy is the energy of the photon, which can be represented by the honey, where high is the Planck constant and the ni is the frequency. Then we can also write as Hc over lambda. Lambda is the wavelength, Planck constant, and the speed of light. Then you can get something like this expression. And this is solar spectra as a function of the photon energy. Here, of course, it's important to say that we look as a solar irradiation only in the form of the photons. But also, sometimes is useful, and we can also consider to watch the photon flux density, and we define this as a number of photons per area, per time, and per energy. And if you divide it power density by the energy per photon, then you can look something like this distribution. So basically, N of E you can characterize like a number of photons in a function of the photon energy. And here you can see basically how it looked like for the IM 1.5 and how it looked like for the black body radiation. And here you can observe that the function have some maximum, and they basically concern all the different photon energies, so from 1 to 4 electron volts. We go now further because for photovoltaics, it's quite interesting basically to find out how many photons can be useful for your materials and how many photons basically can cause your photovoltaic effect. And we're going to see further that, for example, for instance, only the photons which they have an energy larger than the energy your semiconductor material that you use in solar cell can be used to cause the photoelectric effect and can basically create the energy, create the electricity. And here, for instance, we can integrate to find the photon flux in a given energy range. So here, the integration curve are given basically for silicon, because the silicon have band gap, which is somewhere around 1.1, and then you integrate from 1.1 to infinity, and then basically you get something like this curve. And this colored part, so from here, it's basically represent all useful photons, which they have an energy which is above the band gap for the silicon, and you can use them to cause the photoelectric effect and to get basically the current from your photovoltaic devices. And here, number this on this slide, on this right side, you're getting by integration tell you something about the number of the photons which they have enough energy and we can be used for your basically silicon solar cell. This will be, of course, important when we discuss about the PV efficiency. And now something to tell you shortly just about the atmospheric effect. So here you can see basically when solar radiation enters the Earth atmosphere, a part of the energy is removed by the scattering, absorption by air molecules, clouds, and the particles which we often call aerosols. The radiation that falls on the surface directly is called the directly beam radiation. The scatter radiation, which reaches the ground, is called also diffuse component of this radiation. And some of radiation may reach and received after reflection from the ground. Here is the reflection from the ground, and we call this albedo. The whole amount of the radiation that reaches the ground is very variable, and it on many factors, for example, weather condition, air pollution, the time of the year, the time of the day, and of course your location. And approximately in this area, about 30% of light is diffused, average of the year. Plus photovoltaic panels, so here basically can use this also diffuse light. That's why and actually later you basically have in iron 1.1 spectra also diffuse component. However, for concentrating system, we can relies on focusing directional light channels. So this is the concentrating system, usually reaching by optics, where you increase your intensity of light much higher than the standard testing condition are, and to basically get higher efficiency. But this is only mentioned that you cannot use this diffuse component. You can use only direct light. And here is I plotted here how it looks like the all three spectra, and here you can see basically that the RM 1.5 spectra include direct radiation, diffuse radiation scattered from the air, and also diffuse radiation which is scattered from the ground. And here basically you can see what it means when we said RM 1.5. This is the solar irradiance on the surface of our Earth is also determined by the sun position relative to the zenith and the thickness of the atmospheric layer. The loss of the solar radiation in the atmosphere from differences in the solar zenith angle, and it's defined by air mass. And here when the sun is in the zenith, here you have M, which is above the atmosphere, and if the sun is vertical, then you're going to have without atmosphere effect. We take M 1.5, which is no noted here on the picture 48.2.
Even just we are a bit losing your sound. Maybe just to I cannot hear you well. I hear you, but not really well.
You don't hear me well.
Yeah, now I can
Is
hear
that?
you well. So now is okay.
Aha,
Just
now you can. Aha, okay,
maybe you
okay.
just are further from the
I,
microphone or something.
okay. I move a little bit my laptop. I
Mm-hmm.
apologize. So, okay, just said if you don't hear me well. So this is basically to show you the electromagnetic radiation and electromagnetic spectra. Here you have a wavelength. As you can see, we have a lots of large range from the really large one, 10 to the really small one, 10 minus 12. And here is the basically the part of the spectra which is visible and where the sun is the most in this and where for which we are the most interested. So when we're talking about electromagnetic radiation, then basically we have here you show on the picture. So you have a electric field, then perpendicular to electric field, you have magnetic field, and the movements basically of your electromagnetic radiation, it's normal to the both field and electrical and magnetic field. And this is looks something like this. So if it is electric component, this is magnet, then movements is basically normal on the both field and electric and the magnet field. And every electromagnetic radiation basically is characterized by the wavelength, then the frequency, which can be expressed as the speed of light over the wavelength, and of course the photon energy, which is expressed by the high knee, where the high is Planck constant and knee it's a frequency. Of course, photon energy extremely important in explanation of the function of the solar cell, and we're going to see that further. Okay, now we're going to say something about the world power sources, solar power potential, and this is the global energy usage with solar resource. Basically, look the surface, because the surfaces in this first picture are quite important. This is basically the oil, natural gas, coal, then we have a hydronuclear, and these surfaces represent the solar power potential, heating only 3% of the Earth's land, harvested with 50% efficiency. So generally, if you look now this one left picture, so here you can see basically how many more potential we have concerning natural gas, oil, uranium, coal. And here you have a sun, which can give you basically 23,000 terawatts. We use only around 50% of terawatts. And generally, in 2019, only 11% of the global primary energy came from renewable technology, and around 1% of the global energy came from the solar technology. So basically, now the solar and the whole renewable technology are only one small part from the whole energy that people use. But the sun is basically the only source of energy which can replace all of them. Just we have to find a way how we can use the solar energy better than we use now and more efficient. Now we see something about the world-side solar resource, of course, because this is the USA and Serbia project. I will more concentrate on the US and at the end on Serbia, of course. And here you can see basically this is the world map. And here you can see with different color annual average solar irradiance presented in kilowatts per meter square. And here you can see basically that the dark red area are basically the best area for the solar energy, and basically estimate of the available solar power. If we use, for instance, the 10% of unused land, and one of the half of which is covered only by the 10% efficiency of solar cell, then we get something like 80 terawatts available. Of course, the 50 terawatts that we use, it's proportional, for instance, about the solar array, which is long, something like 780 kilometers, which is quite a lot. And this is, for instance, the USA, which is quite good for this application, for the solar cell application. And here I put, at least I found on the internet, that one of the best country for this solar cell, it's Arizona. This is Arizona. And basically, as we called previously, to make something like 11,300 watts, each person need a PV around about 60 feet on a side, so the stuff get to be cheap and abundant. So the silicon is quite abundant element. This is, for instance, the Serbia solar power sources, and this is the number of hours of solar radiation on the territory of Serbia is between 1,500 and 2,200 hours per year. And the average intensity of solar radiation is about 1.1 kilowatts per meter square per day in the north to 1.7 kilowatts per meter square per day in the south during January, and from 5.9 to 6.6 also kilowatts per meter square per day during July. And the average intensity of solar radiation is something like 1,200 kilowatts per meter square per year in the northwest of Serbia, and it's going up to around 1,600 kilowatts per meter square per year in the southeast of Serbia, while in the central part is around 1,400. Serbia has a significantly higher number of solar radiation hours than the most of European countries, and the southeastern part of the country has the best condition. Here is something which you previously also see. So this is from the renewable energy technology, how much PV solar photovoltaics United States using and how much Serbia. I really tried to find out, and I saw that in the last 2-3 years, so basically more than 100 megawatts of solar power plants are put on the roof in Serbia. Then I found one of the PV basically plant which is installed a couple of years ago, 61 hectares in one of the town in Serbia, which you call Niš. And I also found that one of the companies, so CVP Global, announced that will develop 2 large wind and solar projects in Serbia, capacity of 450 megawatts, which 300 megawatts will be wind power plant and 150 megawatts will be solar plant. This is some of the solution basically for the roof and for the industry that has been installed. And I thought, let me just to try to do this. I wanted to show you if I succeed some video just to see how this look like on the video. That's what I'm planning. Simply, I don't know why. Let me just for a second to try, please. Once more, I can succeed. Okay, maybe. Can you see this? Hello, can you see
Yes, yes,
this?
we can
Yes,
see.
we can see.
Yeah.
Yes.
Okay. Okay. I'll stop you. So, okay, maybe one more if I also succeed. Hopefully, I succeed also. Yeah. Okay. Now we return to the presentation. I hope you can see it all. Hello?
Yes, it worked well. Yes, it
Okay.
looks good.
Okay, please give me some indication that you're here. Okay, and now we are going on the second part of this presentation, a little bit more physics, more serious physics, semiconductors and the semiconductors physics. So basically here we give something, we talk something about the band gaps of the common PV materials, which they are already in industry, so not something which is on experimental level, but really something seriously that's have been used in industry. But let me say something about this first. So this is, you have a scale of electron energy, and this is presented basically the valence band and the conduction band. And the difference between the top on the highest level or the highest level of the valence band and basically the difference between the lowest energy level of the conduction band represents something which we call band gap. When temperature is 0 Kelvin, then your valence band is completely full with electrons and the conduction band is completely empty. And if you have if the temperature is larger than 0, then some of your electrons from the valence band will be promoted to the conduction band, and on the place of the electron in the valence band will remain some of the holes. And as we already said, the photon with energy above the band gap can exceed carrier from the valence to the conduction band. So the basically only the photons which they have an energy larger than this Ag or this one value which we presented now for the different solar cell can basically cause the photoelectric effect. And here you can see some of the mostly interesting material. Crystalline and amorphous semiconductors is basically, and their band gap. And crystalline and amorphous silicon is something like a 95, 97% in the market. Then there is also quite applied thin film cadmium telluride with quite good band gap, 145. Then copper indium selenides. Then here is also CHGS and also CZTC, which combination of the copper, indium, zinc, gadolinium, and selenium or tin. And then we also have the gadolinium arsenide and indium phosphide. And now we're gonna tell something why we choose exactly this value of the band gap, or why these semiconductors are really suitable, or other semiconductors which also have band gap in this one range. So for instance, for the silicon, so you can see, so from the 1.1 and the higher energy, so you can see basically that you have enough large number of the photons with enough energy that can cause the photoelectric effect. If your band gap is if you choose that the band gap is too high and not in this optimum area, then the number of the photons which can cause the photoelectric effect will be too small. And if you choose that your band gap is too small, if you go below the one, then you get more photons, but you can extract less energy from each carrier than if the band gap were larger. That's why in this area from somewhere 1.5, 6, we choose the semiconductors to have this kind of band gap, these values. And basically, let's we talk now, we keeping this presentation only on the mostly semiconductors, which they are on the market now. And as you can see, the most used silicon and also germanium, which is quite popular, is in a 4 group in a periodic system. Later we show why It's basically nice to be in a 4 group, but you can also use in combination, which average is 4, something which is indium arsenide, which is a free 5 group, or you can use 2,6, which average is again 4, something like a cadmium telluride, cadmium tel. And for instance, if we look basically the crystallographic structure of the group of the 4 elements, or at least which is average 4, as I show you, 3, 5 or 2, 6, then basically they are covalently bonded and have a structure with tetravalent units with 4 nearest neighbor. And I show you now, if we take this diamond cubic crystal lattice, which is presented on this picture, and here you can see the film, where you can see in details this structure from all different sides. Then this structure have a carbon, silicon, germanium, and modification of tin, which we call gray tin. And here we see that every atom, so for instance, these 1 atoms have a 4 nearest neighbor, as here is described. Here you can see that is the 4 connection. And also for this group is maybe visualized as 2 FCC with 1 translate along the body diagonal. So that means basically that you have every atom of every corner of this cell, and also you have 1 in the middle, which represent basically the diagonal of this side of the crystal lattice. Lattice, then this lattice is relatively closely packed. Atomic packing factor is somewhere around 34%. And compound semiconductors often have a variation of the diamond cubic called zinc blend, named after zinc sulfide, where, for instance, 3,5 gadolinium arsenide atoms alternate. So you can have here, for instance, gadolinium, and on the other place you can place, or you can have arsenic. Let me say something about the material classification by conductivity. And here express the conductivity by delta, and it's 1 over omega times centimeter. And here you can see basically that materials we classify as the materials with very low conductivity, which we call insulators, and very high on the other side conductivity, which we call metals. Somewhere in between insulators and metals are semiconductors. Also, in the construction of the solar cell, we also use the metals and insulators. Basically, the heart of the solar cell represent the semiconductors, and we tell why is that. So the semiconductors are interesting because, for instance, the conductivity is controllable by addition of impurities called dopants. The conductivity in semiconductors is strongly temperature dependent and increases as the temperature increases. For instance, compared to metals, which have a really good conductivity, but their conductivity decreases with the temperature. In semiconductors, basically the story is completely opposite. And here we can see also on this increasing energy scale, basically how this looks like in the metal semiconductors and insulators. And here you can see that in the metals, you have basically the overlap between the valence and the conduction band. This is the semiconductors, where you can have some, which we call energy gap. So the difference between the highest valence band and the lowest conduction band. This is a semiconductor. And you have an insulator when your band gap is much higher than a semiconductors. In the middle of the energy gap, or this gap, generally it's Fermi level of the Fermi energy. And here, for instance, you give the Fermi level lies in the gap between these bands. And for instance, and the temperature, which is 0 Kelvin, the all electronic level in the valence band are full, and all conduction band is completely empty. And if the temperature, and if you increase the temperature, if the temperature is higher than the 0 Kelvin, then some electrons, as we already said, can be promoted to the valence band, to the conduction band. And that allows semiconductors to conduct. So conductivity is very strong, temperature dependent, as we can see. So now we go to define what is basically conductivity. So a closer look of conductivity. Use this equation where the current density is defined or equal the conductivity's time electric field. And if we use physics of solid, here you have some solid or some length, and then you connect on some voltage, then you're going to have some charge carrier number in this solid, and that we usually represent it as a number of the charge carrier per meter square. If we apply some electric field, and the electric field can be basically expressed as a voltage over the length of the solid, that can produce force on a carrier, on the charge carrier. And that force is given as a charge times electric field. This is charge just per carrier, and for the electron, this is the minus E. And we said that the motions of the electrons is responsible basically for the electrical current and in conventional metals and semiconductors. This is basically the basic definition of the electric current. So movements of electron under the electric field. And then we go further. So we came up to this equation, which is this force, which applied on a carrier. And now we continue. If you apply force on the charge carrier, then you have or you induce a drift velocity. This drift velocity we call the average velocity. And average because if we take the Newton's law, force make things accelerate. And on the microscopic basis, for instance, if we apply force to a particles, then that particles will accelerate, then it will scatter, then will again accelerate, then will scatter again, and that we call this average basically velocity. And this average velocity is defined by the mu force over the charge, and this is mu times electric field. This mu we call carrier mobility, and this is the quite important material property. And if we call now that the drift changes cause the current density, so by using this equation and by using carrier mobility, current density we can define as the carrier density, then charge, then times carrier mobility and electric field. And if we use the Ohm's law, then the current density we can define as the conductivity times electric field. And this is also can be expressed just using by this simple equation as the carrier density and carrier mobility. And it's quite logic because the conductivity from here, conductivity will be higher if your charge density is higher and your carrier mobility will be higher. Of course, then, and the conductivity will be higher. So the conductivity is related to the carrier density and carrier mobility. And this is just units of mobility, which is from here, it's quite easy to take. So that's average velocity over the electric field, and you get something like a meter square over the voltage time second. Now we tell something about the electrical properties of the solids. This is also important for the characterization of materials for photovoltaic devices. And from the beginning, we also start from the very simple Ohm's law, where basically where we define basically that the voltage is current times resistance. And if you have here the solid, and this is the where your current going, this is just the voltage, and this is we call cross-section area of the solids. Basically, resistance, which we measure in ohm and which is volt over ampere, because resistance from here is just a volt over current, so it's volt over ampere, is a device property and depends on what the device is made of and also on its physical dimension. We can relate this to a material property, which we call resistivity, which a part of conductivity is also quite important value to define when we talk about the photovoltaic material. So basically, resistivity is defined that resistance is equal to the resistivity times length and over cross-section area. And from here you can see that basically the larger resistance is if we have a larger length and if we have an area is smaller. Okay, now we more or less define what is the resistivity, and if you take basically the other definition of the Ohm's law, and this is just from this equation, that the current is a voltage over resistance, then you can define the current density, and current density is always current over the cross-section area. And here you can basically get something like this by using this expression for the resistance. They're just a simple equation. And then basically you end up with voltage over length, which is electric field over the resistivity. Of course, the electric field is also more generally, so just the negative gradient of the voltage. And this one can be connected because the 1 over resistivity is conductivity, so we can basically say that our current density is conductivity times electric field. And it's logic, so when your resistivity is high, then the conductivity is low and opposite. You can basically follow from equation what is happening. Now we go further, that we can understand the free electronic model and how basically the electrons are how the electrons are placed in some atoms in the crystals, and how we can understand the whole process and the conduction and the valence band and what is exactly happen. We have to understand something which we call density of states in the bands. Basically, we said that the bands can have different number of states per energy, and we call this density of states. For instance, on the left side, you have a smaller number of states, and that we call the low density of states. And here you have a much higher number of the density of states, and we call this high density of states. Density of states is generally defined as the number of electron quantum mechanical states per volume per energy. And density of state, this function here, d of E times increment dE, is just the number of states between the energy E and E plus increment dE. So for free electron bands in a solids, the density of states varies with energy within the band gap. So if we look here how it looks like compared to the energy, the density of state increases with energy. That means that you will gonna have a higher number of the states at a higher energy, and you're gonna have a smaller number of the states at a lower energy level. And here is basically, if you present it on the diagram, on the dependence, how your density of states look like in comparison to the energy. So you can see that is basically exponential dependence, and it's grow exponential basically thanks to this expression, which is a free electron density of states, because you see that the density of states depends on the square root of the energy. And here you just have a constant P, then M, which is electron mass, and you have reduced plus Planck constant, which is Planck constant over 2 pi. Now we go further. And we're gonna try basically by using also the free energy, free electron picture, try to understand basically how we get the valence and the conduction band. And we're gonna see how it looks like with taking atoms and putting them together to make a solid plus free electron picture. And here you again have some energy scale. And here you have two isolate atoms, and which every of these isolate atoms is represented only by one energy level for easiest understanding. And if you bring this atom together, then you're gonna get higher and lower energy level. Then you get a two energy level on which the lower, which we call bonding, um, excuse me, lower, which we call bonding, basically have a lower energy than the previous isolate atoms, and anti-bonding, where basically you have a level which have energy higher than the previously energy levels of the isolated atoms. And what is happening if we put, for instance, the four atoms, isolate atoms, then if you put them together, then you're going to get very similar picture. Just now you're going to get the pair of the higher and lower energy level. This is the, again, pair of the energy level with the lower energy than the previous separate atoms, which we call bonding, and again, pair of the higher energy level, which we call antibonding. And what is happening if we took a lot of atoms and bring them together, then you get something like lots of lower energy level, which we call the valence band, and lots of higher energy level than the previous energy, which we call basically conduction band. So from the bonding, we create the valence band, and from the anti-bonding, we create the conduction band. And I think we said everything what we need. As many atoms are brought together to make a crystal, that's, I think, completely clear. Atomic electronic states are split to have different energy. We also saw this. New crystal electron levels are grouped into bands or narrowly spaced energy level. We also show this. Anti-bonding states become the conduction band, and the bonding states become the valence band. Describing electron in solids. Now we said something about the electrons described by the quantum mechanical state. And here on the right side, you can see basically quite nice picture, which many people show. Electron states in quantum coral made of iron atoms on the copper surface. It's made by the scanning tunneling microscopy, and that's the type of microscopy used for imaging surfaces at atomic level. And here, what you see basically, it's copper surface, and here up are the iron atoms, and here cycle inside are electronic states. So one really nice picture. So basically, those states describe the energy of electron, its momentum, which we define a little bit later because we cannot define everything in the same time, and then define the probability of finding it at a given location, and the property of an electron known as a spin. And this spin can be either up or down. So the important characteristic of every electronic state are the energy. This gives the energy of electron that occupies a given state. Every state has different energy value. So here you can see different energy states. And that different energy states have different energy, which you read on these lines here, which they show you energy which increases. And then the occupancy, which they said, for instance, here we show how we put 6 different electrons some atoms have. So this is electrons in every level with spin up and spin down. But let me say something which is quite important. So each state can be occupied by either 0 or 1 electron. Electrons with different spin are basically different states. That's why on the same energy level, we can put 2 electrons with a different speed, because every electron with a different speed representing a different state. And states with a given energy can have a fractional energy occupancy between 0 and 1, which we already mentioned. Now we try to understand how these states, basically density of states, are occupied in the different situation. This is when we have basically on the temperature, which is 0. Here is the equation for the density of states. This we already see how it looks like density of states in the function of the energy. And here is for the 0 Kelvin is basically equivalent with the picture I showed you earlier. These field states are basically the valence band, which is completely full, and these empty states here below the curve are basically conduction band, which is completely empty on the 0 Kelvin, and exactly the energy which correspond to this border or the highest occupancy field state, we call basically the Fermi energy. And if we imagine, if we put in n electrons per volume, electrons field state in order of energy. Now it's a question, what is the energy of the highest field state? And we can get this by just integrating the density of states. And then here we get, because we integrate to the Fermi energy, so in this expression, basically, we get a Fermi energy, and this Fermi energy we can arrive from this equation, and it basically depends only on the constant here. Again, reduced Planck constant, and here is basically number of electrons per volume. And if you want to, for instance, just to have some feeling, just to calculate, for instance, for one atom, such as the copper example, which have 1 electron per atom, then you can get the number of electrons per volume is 4 over A cube, where A is the lattice parameter and 4 is because copper have FCC, so the 4 atoms on the every side, and then you can get something like a Fermi energy is 7 electron volt. And to have some feeling what is the temperature that correspond this Fermi energy, so we can basically find very easily, because at the room temperature on 298 Kelvin, 0.259 electron volt, and from here, basically, we can get for the Fermi level of the 7 electron volt, basically correspond very high temperature of 82,000 Kelvin. Okay, now we're gonna see what is happening when the temperature is higher than 0 Kelvin. So then when you can basically promote your electrons from the valence band to the conduction band. Then electron states are occupied according to the equation or distribution that we call Fermi-Dirac distribution. And this is the Fermi-Dirac distribution. Basically, it's quite simple equation, which depends on the energy, temperature, and something which we define and call chemical potential. This chemical potential is basically also called the Fermi level, because it's temperature also dependent. And for the temperature, which is 0 Kelvin, Fermi energy is completely name as chemical potential. And if we want to present basically this function in a function of the energy for the different temperature, here you can see this function we also define as the probability that a given state will be occupied. And for instance, for a zero, so you see basically that probability is on the maximum and sorry, I forget. And then on the 0.6 electron voltage, this is relevant chemical potential for the silicon, then basically drop to zero, and it's completely zero because you don't have, for a 0 Kelvin, you don't have any electrons in the conduction band, so only in the valence band, and that's why the probability that some state will be occupied its maximum. And it's dropped exactly on the Fermi energy, as we already see, but the Fermi energy for the temperature 0 is basically the same as the chemical potential. So this is the 0.6 electron volt. But what's happening if you increase the temperature? So if you increase the temperature, then your curve basically is changing, or you decrease the probability that you can find any more electrons in a valence band, and basically you increase the probability that you can find electrons now in the conduction band. So it's changing, or you increase the probability that electrons will be below the Fermi energy, and you increase the probability that electrons will be above basically the Fermi energy. And this is how you can also, the same picture, you can present it as a density of state in a function of the energy, where you, for the 0 Kelvin, you have something like just line which they drop on the Fermi energy, but this curve is changing when the temperature is rising, and here you have something like this. So this this can be observed as a valence band, and this as a conduction band. So the here, by increasing temperature, we decrease the probability that electrons can be observed in the valence band, and you increase the probability that electrons can be observed in the conduction band. And that transition usually that transition is within the thermal energy. So this one part is within the thermal energy, which is defined by the Kb times Tt is the temperature, and Kb is the Boltzmann constant. And I think it's the last slide for today, for this evening or for this morning, whatever. I think it's enough. We just observe how it looks like the free electronic picture, and we try to define something as momentum, for which I think it's quite important. This is the band theory, basically, of solids. And if the atoms give up outer electrons, creating electron C, and charge remain atoms' cores. Electrons behave as though they are particles in a box. Mass each occupied in its solid state, electrons are fermions, and interaction with positive atoms, cores, and with each other. So basically, if we look at some solids, and this is a positive ion core, and this is electron clouds. So free electron model says that there is no interaction between electrons and ion cores. And if you don't have interaction between electrons and ion cores, that means that electrons have only kinetic energy. There is no potential energy in this case. And if there is no potential energy, then kinetic energy just can be expressed as 1/2 mv squared, and then can be expressed as p squared over 2m. P is basically classically momentum, which is also can be expressed, but mass times the speed. Or by quantum mechanically, by using the Broglie wavelength, And because of the fact that the light can be also observed and as a wave and not only as a photon, we're going to define basically the Broglie wavelength, which is the which is a Planck constant over the P, which is momentum. And from this equation, it is completely clear that the momentum is basically Planck constant over the Broglie wavelength. And if we write this equation by just multiplying and divided by 2p, then here on the left side, you're going to get the Planck constant, and on the right side, you're going to get something as a wave number, which we call basically the wave number. So the free electron energy can be expressed in a form of the wave number, and if you draw something like this energy in a function of the wave number, you can see that you basically get one parabola. Also, because the momentum is directly proportional to the wave number, this is also dependency and from the momentum of the energy. So that's more or less for today. Thank you for your attention. Hello?
Thank you for the presentation.
Thank you very much, Ivana.
Okay.
We have at least 5 minutes for discussion or questions. Does anybody have a question? I think there was so much great information in there. If someone was paying careful attention, they could have 20 questions maybe.
I don't know, but I said that the photovoltaics is not only the nice picture of the solar cell, it's also in the physics behind that. So maybe, I mean, I try to be simple as possible. At least I really try. And maybe, I mean, now it's lots of information here, but basically on the second, third,
Alexander has a question.
When you repeated, some of the fiction and that kind of stuff, I think it will be already in the head, way of thinking at least.
Right. Alexander has a question.
Alexander.
Hello, very nice presentation. And I have just one question. Is there any perspective for upconverting nanoparticles to increase the efficiency of the solar cells? I mean, there is a research ongoing regarding that, but how far is it from being actually applied on the solar cells?
Upconversion. So I honestly, I don't know, I already know this, but I didn't follow so much upconversion. I mean, I know that some of the scientists doing on this subject, and I even listened some of the presentation, but I don't think so that I can comment you now how far we are in that way and on that field.
I can comment on this. So in addition to upconversion, there are also efforts and studies on downconversion and on plasmonic enhanced absorption. And I have not seen any studies on state-of-the-art high-quality solar cells that show that these methods can improve efficiency, but let's assume that they can. Let's assume that someone takes a high-quality silicon solar cell and shows that with down conversion, for example, maybe taking multiple infrared photons, they can generate some additional photons that silicon absorbs, and they can improve the current, let's say. I think that the likelihood in the near term, meaning maybe the next 10 to 20 years, of this being able to be integrated economically into a product is very remote, low probability, because the costs are bound up in reliability and manufacturability, and it's going to add complexity to your system. So I think from that standpoint, the research is interesting and important, but maybe a bit more long-term research at this point.
Yes, I agree completely with Randy. I mean, it's interesting, really. At least the talk I listen and everything else, but I don't think that they haven't done something seriously concerning this that now we can discuss how far they go with this. You have something else?
Does that answer your question, Alexander?
Well, yes, completely. Thank you.
You're welcome. Dragan, you understood everything?
I cannot hear you, Dragan.
Yeah, it was a great presentation, even obviously much
thank
of
you.
physics and physical chemistry that I learned a long time ago. Now I have a need to ask as somebody who is not English in this field. Obviously, we rely most on silicon solar cells, but I wonder, besides those materials that I showed in one of the tables, you know, with silicon and cadmium telluride, are there any attempts to involve, you know, metals in terms of, you know, using them for solar cells? Obviously, I remember, you know, some of the discussion that you mentioned about balance and conduction band, but I just wonder, you know, obviously this kind of, it's in line with the question about nanoparticles too, you know, is there a solar cell that is made of metal? Or is that possible at all?
As far as I know, no. Randy?
To be able to generate
I mean,
a voltage,
that's
you
not
need
possible.
to be able to create separation between what is referred to as the quasi Fermi levels for electrons and holes. And without a semiconductor band gap, this becomes, you know, it's unclear how you could use a metal to do this.
Yeah, that sounds reasonable.
I show you on the slide that in the metal you have overlap between the valence and the conduction band.
Yeah, yeah.
And only in semiconductor and insulators you have a difference. I mean, you have a gap.
Band gap.
Okay, insulators have a too large gap that can be, I mean, considered, you know, for the photovoltaics, but metals have overlap between the valence and conduction band.
But this sounds to me like when I read about history of solar cells, they like said that they firstly noticed this effect in a metal in electrolyte solution lighted by sunlight, so that they registered some voltage. So it was on some metal.
Yeah, I think photoelectric effect originally was discovered in metal systems, like say sodium, I'm not sure.
The photoelectric effect is a bit different than the photovoltaic effect. The photoelectric effect technically refers to liberating electrons from a metal electrode using light with sufficient photon energy to overcome the work function of the material. And you're right, Nicola, I think the earliest examples of photovoltaic properties are based on maybe selenium or vitreous selenium.
Yes, that's selenium.
And the details of how that worked, I think selenium may be a semi-metal, so it may have a small band gap, and so it's not really a pure metal.
Sounds good.
Yes, selenium. Is there any other question? I mean, you can ask whatever you like or something, which, I don't know.
Okay, great. And I just had one comment, Ivana, on your earlier slides. You did a really nice job describing the relationship between the solar spectrum and current density, and you know, in both in terms of the solar spectrum, in terms of photons per unit area per unit of bandwidth.
Energy. Yeah.
There was one, you were referring to irradiance with units of watts per unit area per length or per unit of bandwidth. In evaluating the properties of solar modules and solar arrays, there are some irradiance measures like global horizontal irradiance and direct normal irradiance. And those are typically addressed in terms of an intensity or just watts per square meter. And when I'm teaching this and we're talking about the spectrum like you were, I refer to that as spectral irradiance. So it's just a small differentiation between irradiance and spectral irradiance.
Oh, no, okay.
So in one case, it's just watts per square meter. You're typically, you know, working with actual sunlight measurements. And in the other case, you're talking like you were, you're talking about the importance of how the irradiance is dependent on the wavelength of the light.
Yes.
Yeah. So I'll talk about irradiance a bit in modeling energy generation from solar arrays later. So we have another presentation next Thursday at noon from Professor Istalovic from Dragon. So maybe it's time to sign off because we're about 5 minutes over time. Any other comments, Ivana? Dragon?
Yeah. No.
Let me just, but don't forget to stop recording it.
Uh-huh.
I think it
Are
will
you